Hello, this is Dr. Kraus with a video on root locus control design. My students had started a project and we had not yet learned very much root locus theory, and so I basically showed them how to generate a root locus using a computer and told them to try some educated guess and check and see if they could come up with root loci that looked good. That process got a little frustrating, understandably, and I think we now have enough root locus theory to talk more about how to do design. So I want to consider for our first example this underdamped second order system. The poles of this system are -1 plus or minus 4j. So if I were to plot those on a real versus imaginary axis, it would look something like that. And if you've got any background in root locus at all, you know that if we just did proportional control, these would just go straight up and straight down. The damping ratio would decrease proportionally, and the natural frequency would go up, and the zeta omega n product would stay at -1. My settling time would never change. Basically, nothing good would happen for me. So if instead I decided I wanted to require that my poles pass through some desired point, and let's call this point -4, 4j, 1, 2, 3, 4. So if I said I must have my root locus pass through that point, the question would be, how would I know what form of controller to even try? And then how would I do the calculations to choose the coefficients of that controller to cause my root locus to pass through that point? And the key issue, as in all things root locus, is phase condition. So if I want this point to be on my locus, then my phase, so I'm going to call this point S0, my phase at S0 has to equal plus or minus 180 degrees, plus or minus n times 360, and my phase at that, or kind of any point, would be the sum of the phase from my zeros, and right now I don't have any, minus the sum of the phase from my poles. And so the first question we would ask is, do I need to add a zero or a pole or some combination to get the root locus to pass through that point? So the first thing I would point out is that if I call this phi1, the angle from this top pole, well, phi1, since this is straight over, is 180 degrees. And then if I also defined a phi2, that is this angle from the bottom pole up to there, a couple of different ways you could get at that, but there's a 90-degree angle here, and then we go up 8 and to the left 3. And so we could say that phi2 was equal to 90 degrees plus the inverse tangent of 3 over 8, for example. And so it turns out that phi2 is 110.56 degrees. So it should work out that the phase of my transfer function with just the two poles at this point is a -180 minus 110.56, or a -290.56. And so the issue is, whatever term I add to my controller has to bring this phase to -180 degrees. So maybe I should say it's clear in my head, but maybe not clear. I'm operating under the assumption that I have some D that I need to design. I already have this G, and we're putting this under some kind of unity feedback like so. This is my output. This is my closed loop input. So if I'm already at -290 and I need to be at -180, hopefully it's clear that a pole would only make this situation worse. A pole would give me more negative phase and take me further south from -290. Maybe you could get to -360, but that's a little bit of a philosophical thing, and it's not a terribly good idea. So it turns out I'm better off trying to add a zero, which is kind of like doing PD control, which will make some control educators kind of cringe a little bit. We'll later turn it into a lead compensator. But for now, let's assume a PD control. So I'm saying that my D of S is KDS plus KP, which I'm then going to factor out the KD and rewrite in this form, K times S plus Z. And so Z is the location of my 0. And what I need is that the psi from that 0 would be 110.56. Right. No, that makes sense. I'm like, why is it exactly the same? Well, I already have a negative 180 coming out of this phi 1, so I need to kind of exactly cancel the phase contribution of phi 2 to get back to 180 degrees. So what we're saying is, how do I use this to solve for a z that causes all my psi to be 110.56 so that my phase goes to 180. So somewhere in here, we would have our 0 from our PD controller, and this angle needs to be 110.56. Let's redraw that on another axis to try to clean it up and keep it from getting confusing, or more confusing than it already is, perhaps. So here's my test point at negative 4, 4. And we're saying we have some 0 location, and this is 110.56. And I know that this distance is 4. So the tangent of 110.56 degrees is equal to 4 divided by my adjacent distance, or A is equal to 4 over tan of 110.56 degrees. And so it turns out that that will be a negative 1.5. So this 0 location, this is also 4, based on our desired polar location. So 4 minus 1.5, we're saying that Z here is 2.5. So that would be a negative Z, actually, sorry. So I'm saying that my D for my controller, D hat, would be S plus 2.5. And then my overall D would be some gain that I'll solve for later times S plus 2.5. So the key issue is recognizing that the phase that we had is below negative 180, and so we need to add phase to make our root locus pass through that point. And the way that we add phase based on this definition of the phase of a transfer function is to put in a 0 or a lead compensator, and we'll do lead compensator in our second example. So the question is, can I then prove that if I have this 0, my new root locus, which would look like this, will now in fact pass through my desired test point? Let's flip over to Python and see if we can show that that's true. So let's work through this same problem in Python so that we can carry it through to a numerical completion and verify that we pass through our desired test point. So I'm defining my transfer function, looking at its poles, proving that they agree with what I asserted at the start of the video. And then this is the open loop root locus, as I mentioned, going straight up and straight down, not really giving us a desired behavior. Defining our test point that we want the root locus to pass through of a negative 4 plus 4j. And then these are the phase angles that I presented when I was doing the paper and pen part of the video for phi 1 and phi 2. So when I add those together, I get the negative 290.56 that I talked about. I'm not sure what that is, so pay no attention to that. So I need my 0 from my PD controller that I'm about to add to get me back 110.56 degrees of phase so that the overall phase would go to negative 180. So if I do the same calculation we talked about, I get a 1.5 offset from my desired pole location. So I end up with this PD controller that is has a 0 at 2.5, basically saying that my proportional gain should be 2.5 times my KD. or derivative gain. So then defining that d hat times g as my L, and generating the root locus of that, I get this, and you can see that it does in fact pass through -4, 4, which is our desired pole location. And then the next question should be, what k value do I need to put my root locus at that point? Use the magnitude condition. So if this is the magnitude of L, or I guess more specifically, if I really want to talk about the magnitude of L, yeah, I mean, that is the magnitude of L. The other thing to point out, though, our goal is that L should have phase of -180. So you'll notice that it has negative real part, and the imaginary part is essentially a floating point 0. Okay, so if 1 plus KL has to equal 0 for a root locus, and this is the magnitude of L, then K has to be 1 over that. So in fact, a K of 6 should put us at our desired pole location. And if you wanted to, you could rerun this root locus going out to a K of 6, and you would see that this branch stops right there, and this branch stops right there. I'm going to find the closed loop transfer function using my K1 of 6 times my L. And in fact, my closed loop poles are -4 plus 4j. So I have succeeded at putting my poles where I want them to be. I could then also do a step response of my closed loop transfer function, and it looks like this. Now, because I've got a 0, I probably have more overshoot than I was expecting, and I also don't have a steady state error of 0 for a unit step input, so that would require some additional work, but this is a pretty good starting point for my control design. So key idea, I picked a target point that I wanted my root locus to pass through, and then when I evaluated all my poles and zeros at that point and found the phase of L, I found that it was -290, so I needed to add 110.56 to that, and since that's positive, that means I'm adding a 0, and so I added a 0 like so. As I mentioned when I was doing the paper and pencil part, we'll use that as a launching off point to talk about how to convert this to a lead compensator design instead of a PD design, so we're doing a better job of not causing excessive high frequency noise, and I'll do that in my next video. Thanks.